So here's again our projection from the group algebra to some invariant subspace by right multiplication with some idempotent E mu. And now the claim is that if we write the idempotent as a linear combination of the group elements, then we can read off the dimension of the subspace from the coefficient of the identity. And we prove this by calculating the trace of our projection in two different bases. So first we choose a basis for the group algebra in such a way that the first few basis elements are a basis for L mu, and then we just continue, say, with q d mu plus 1 up to q order of the group, so that it's a basis for the group algebra. So the first few here, these should be a basis for L mu. Now when we apply our projection, then it takes qj and maps it back to qj if j is less than or equal to d mu. But if we apply it to a qj with a larger index, then we know that we end up in our subspace L mu, so we will get a linear combination, of the first d mu elements. And now this means when we write this p mu here, this projection p here, p mu it was called, okay, it's p mu. When we write this p mu as a matrix, then each of these here gives us a 1 on the diagonal. So there are d mu 1s on the diagonal, and from these down here we get zeros on the diagonal because we never get the thing back which we put in here. So the trace of p mu is just the dimension of the subspace to which we project. Good, and now we want to do this again in a different basis. So let's choose the group elements as a basis for the group algebra. And now let's see what does our, if we start with some, no, hang on. If we take a basis element, so G, a group element, then our projection P mu would map this to G times E mu. E mu is the idempotent. So if we write the E mu as a linear combination of the group elements, then this reads like this, sum over G prime in the group, and then we have G prime, and and some coefficients here. Let's say AG prime. So let me highlight this. This here is the E mu, and over here this is the E mu, and we right multiplied the blue G. And now this term here will be on the diagonal if this thing here, is just G again. But that means that the G prime has to be the identity. So for each group element, we get a contribution on the diagonal which is always the coefficient for G prime equal to the identity. So this means that now the trace of P mu is just the sum over the whole group, and then for each group element I just get the coefficient of the identity. So this is the order of the group times the coefficient of the identity. And if we combine these two here, these two results, then we can read off our claim from up here.